Next up, we wanted to take you through some calculations and some example problems looking at isolated systems where we have our change in angular momentum is equal to 0. So just as a quick review, we basically have two ways we want to deal with collision or changes in inertia type of problems. One where we have an external force or torque that causes a change in momentum. So the torque exerted over a time interval is going to result in a change in angular momentum, much like we look at the impulse momentum theorem in the linear world. Looks just like that, so that's our analog to that. And in the previous video we also looked at different ways that we can calculate the angular momentum, whether it's a particle or an extended rigid body. We take that perpendicular radial component times the linear momentum to figure out the angular momentum of a particle, either moving in a circle or a straight line, or we can take the rotational inertia of an extended rigid body and multiply that times its angular velocity to figure out the angular momentum. So that's kind of where we're starting off. These ideas will certainly come into play when we start looking at isolated systems as well. So isolated system means there is no external force or torque. And we know that the total angular momentum before has to equal the total angular momentum after some type of interaction or some type of collision. And we know as a result that our change in angular momentum is going to be equal to 0. So we want to look at a couple different ways we could model that mathematically and conceptually. So first one I'll start off with, this is a problem that I gave you on a worksheet. This is a dart that collides and sticks with a wheel. So we have a wheel here that's going to have a mass big M. We'll say the dart has mass little m. It also has a velocity equal to v. We'll say that the wheel has an initial angular velocity equal to 0, and it has a radius equal to big R. So let's say, so collides and sticks, so afterwards it's going to have some angular velocity, we'll call it omega prime, and let's say that's what we want to solve for. Well, how do we go about solving this with our given variables? We know that our total angular momentum before has to equal the total angular momentum afterwards. This is going to be the angular momentum of the dart, again, relative to this observation point or this pivot point. So once the dart hits the wheel, it's going to rotate about that axis, so we need to make it relative to that. Plus the angular momentum of the wheel, but that's going to be equal to 0 because it's not rotating, so that thing's just going to go to 0. Our total angular momentum afterwards is going to be just the sum of the two pieces. So you have the rotational inertia of the dart, which is now acting as a particle on the very edge of the wheel, times that final angular velocity, plus the angular momentum of the wheel, which is now rotating, times its final angular velocity. So the angular momentum of the dart, kind of start off with a little more space here. This is a particle moving in a straight line coming across, so we're going to drop that perpendicular as it moves about this way, and that of course is just going to be equal to the radius of the wheel. So the angular momentum of the dart before is just going to be the radius of the wheel times the mass of the dart times the speed of the dart before. As I mentioned before, the wheel is not rotating, so it has no angular momentum. And then let's see, we'll factor out that omega prime, and we just got the rotational inertia of the dart plus the rotational inertia of the wheel. Okay, the wheel is going to act like a hoop, and we can use the rotational inertia of the hoop to be mr squared, and I don't remember if in the problem maybe I said it was a disk and we use 1/2 mr squared, but whatever, you get the idea. You'll be given the rotational inertia of the wheel or the disk or whatever it is. So omega prime, the dart is going to be a particle, which is going to be m. It'll be a distance r away on the edge of the wheel, so r squared, plus mass of the wheel times its radius squared, the dimension of the wheel itself, again following from the rotational inertia of a hoop. So you can see a few things could cancel. You could probably factor out an r here and cancel that out. So we can cancel omega prime r squared m plus m, just to kind of simplify things a little bit. One of the r's will cancel with one of those, and I get m times v over m plus big M is equal to omega prime. So this is how we could solve through just kind of a collision or collide and stick type problem. Another problem deals with rotational inertia of a system that is rotating, and somehow that rotational inertia shifts. So you could think of this kind of like an ice skater. If she were to be spinning and then she brings her arms in closer, we know that the person will start spinning faster. Well, basically all that's happened there is that she has changed her rotational inertia. So in order for angular momentum to be conserved, because it's an isolated system, again assuming no friction between her skates and the ice, she's going to have some new angular speed. So we'll use that idea to apply to a different type of problem. So let's use a giant merry-go-round. Let's say in this merry-go-round has a radius r, and we'll say that it's a solid disk and it has a mass equal to m times d. And let's say we have a person that's going to start at this location, some radial distance away, r1, and they are going to move or walk in towards the center of the disk and end up at some new radial position r2. So let's say they just move along that straight line. I kind of made it off to the side so you can see it a little bit better. So, same idea, conservation of angular momentum. So let's say initially it has some angular speed, and we want to find out what's the final angular speed as that person moves inward. Well, we can just conceptually reason that we know it's going to be faster because the rotational inertia of the system has gone down. So let's look at what we have here. So our total, we want to take our total angular momentum is going to be the rotational inertia of the particle or the point mass, the person, plus the plus the rotational inertia of the disk times that initial angular velocity is going to be equal to the new rotational inertia of the person because they've moved in closer to the pivot point, and the rotational inertia of the disk, which doesn't change, times that final angular speed. So now let's substitute in what we know. Let's say that the mass of this little person here, let's just call it little m. Person is going to be m. They're going to start at r1 squared plus the inertia of the disk. Again, let's call it a solid disk and say mass of the disk times r squared. 1/2 mass of the disk r squared times my initial angular velocity is going to be equal to m times r2 squared plus, again, 1/2 mass of the disk, oh, I'm running out of room, r squared, again, times my final angular velocity. So again, this really just becomes kind of a big algebra problem to isolate your variables and work your way through it. So sorry I ran off to the side, but that's kind of that idea of a particle moving along a merry-go-round. There's one more challenging problem which I'll do in a separate video, and that involves with a collision that causes a rotation, so a linear collision that makes something rotate. So that'll be the next video.